Algebra 1, Section 8.6, Geometric Sequences. What I have here to start is not a geometric sequence. This would be something you learned earlier in the year. In Section 5.7, we discussed arithmetic sequences. Today, the topic will be different, but there are some properties that are the same. The sequence 8, 11, 14, 17, you ought to notice goes up by 3. And what we did at the time was we said, okay, this has a name and it's called A of 1. This is called A of 2. This is called A of 3, etc. Okay. Now, caution, when you get into Algebra 2, the notation changes just a little bit, and they call it A sub 1, A sub 2, A sub 3. Okay. But that really doesn't mean anything. You'll make that adjustment no problem when you're in Algebra 2. In fact, I'm not sure why the book even does that. It's the same textbook series from one class to the next, but they do make that change. Talk about that next year. 8, 11, 14, 17 is an arithmetic sequence because it's going up by threes. To get from 8 to 11, you add 3. To get from 11 to 14, you also add 3. And to get from 14 to 17, you add 3. This is called a common difference. And the reason it's called a common difference, differences in subtraction, is because if I take a number and subtract the previous term, I get that difference. And if that difference is the same from one to the next, 17 minus 14 is 3, 14 minus 11 is 3, 11 minus 8 is 3. If it's the same thing each time, that makes it common. Therefore, it's a common difference, and therefore it is an arithmetic sequence. Now, again, that was section 5.7. Here's how this works out today with geometric sequences, is we can use the same labeling notation. This is A of 1, this is A of 2, that you're just saying what number in the term, what number in the sequence that it is. 8 is A of 3, 16 is A of 4, and the next one is A of 5. Out here somewhere, we don't know, would be A of n. We don't know where that is. It could be 6, 7, 8, 5,000. It's a term in the sequence. I think of these that I have written in blue, I think of them like they're the names. These are the actual values that are in that position, and then what's in blue is the name, okay? And now notice 2, 4, 8, 16. This is not arithmetic like you learned in 5.7, because to get from 2 to 4 would be to add 2. But to get from 4 to 8, you don't add 2. Okay, so there isn't a common difference. Instead, you can probably look at this and realize that it's times 2. To get from one to the next, you're multiplying by 2. And since that's consistent in each case, it is what we call a geometric sequence, not arithmetic, but it's geometric. And the common ratio is 2. So what we just figured out here, this times 2, really just the number, the 2, that is the same thing over and over again, is actually this, the common ratio. And that would lead us to this formula, although let me just do these other two examples real quick. 24, 12, 6, 3, 1.5 is a times 1/2, or 0.5, times 1/2, times 1/2, times 1/2. So that also is a geometric sequence. And something interesting that can happen with geometric sequences is that they can alternate positive, negative, positive, negative, because to get from 5 to negative 15 is times negative 3. But then if you take negative 15 and multiply by negative 3, you're going to have a positive number again. And then this again is times negative 3. What we did in the second example by multiplying by 1/2 shows the common ratio to be 1/2. In this one, the common ratio is negative 3. Now, let me show you one other thing. Let's take that 8, 11, 14, 7 that we started with. I think I showed you this in the year. If I go 8 and I add 3 to it, and this works on your scientific calculators just the same as it works on a graphing calculator. If I go 8 plus 3 and get 11, and then I go plus 3 and get 14, by doing that, you have trained your calculator to know what the sequence is going to be. So now all I have to do is push enter, and it'll assume add 3. All I'm doing is pushing one button, enter, 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 enter. By doing this, this is actually calculating it recursively. That would be an important word. If we were doing this lesson in class, we'd be discussing this in more detail. But let me just tell you in general, just kind of in passing, that the word is recursive. It's something that's happening over and over again. You're adding 3, you're adding 3, you're adding 3. This is a recursive calculation. And I could keep going, just keep pushing enter, and it keeps giving me the next term. Okay. Now the same thing will happen on your calculator. Let's use this 24, 12, 6, 3. If you go 24 times 0.5, it'll give you 12. If you go times 0.5 again, it'll give you the third term in the sequence. Now, everybody understand, 24 was a of 1. 12 is a of 2 because I've multiplied by a half. 6 is a of 3. If I want a of 4, all I have to do now is push enter, and it'll assume times 0.5, and it'll give me 3. The next one will be 1.5, the next one will be 0.75, and it'll keep giving you more and more. And I'd have to keep track. If I were to calculate it this way, I'd have to keep track. Okay, that's the fourth one, fifth, sixth, seventh, eighth. How many times am I pushing the enter button? Okay, this is calculating a geometric sequence recursively. There is a better way, though. Better than recursive is explicit, and this is the one that I put in notes today. A of 1 stands for the first term, okay? So if I were to write this for that first geometric sequence that I gave you, 2, 4, 8, 16, 32, 2 would go in this place right here. R is the common ratio. That's what we calculated. That would actually be 2 as well. 2 times 2 to the n minus 1. If I were going to do this one, actually, let's write that one out. A of n is equal to 24 times 1/2, or 0.5, to the n minus 1. This one here would be a of n, right? Because that's the generic term. That's any term in the sequence, whichever one I want to know. And if I want to know a specific one, I could plug that number in for n. If I want to know the 11th term, I could find a of 11. This is just really function notation being applied to geometric sequences. A of n would be equal to 5 times -3 to the n minus 1. Okay, now the n minus 1 might be a little curious to you. I think an example that we do here in a moment might clear that up a little bit. But basically, we have to increment n down 1 to account for the first term. Okay, so let's just blow through some examples here. Find the common ratio in each sequence. 3, -15, 75, -3, 75. Looks like we're multiplying by -5 each time. So as you go from 3 to -15, it's times -5. Since that's the same thing in each case, and if it weren't, by the way, if it were something else in just one of those examples, then it's neither. It's not arithmetic, it's not geometric. But this is times -5 each time, so the common ratio is that number, -5. Point of fact, it is not times -5. That's not the common ratio. The common ratio is a number, and it's -5. Now, just the same way as I would explain common difference to you, as I did explain common difference to you, I would explain ratio the same way. Why is it called common ratio? You know that a ratio is a division of things. Well, if I take the current term, -375, and I divide it by the previous term, the one previous to it, 75, you'll get -5. 75 divided by -15 is also -5. It's a ratio. Take the current term, subtract the one that's previous to it, you'll get a number, and if that number is consistently the same number, if it's common, then it is a common ratio. Here's an interesting one. 3, 3 over 2, 3 over 4, 3 over 8. Notice that 3 really is like saying 3 over 1, and that the denominators are forming a geometric sequence, okay? What's happening is you're multiplying by a half. If you take 3 and multiply by a half, you'll have 3 halves. If you take 3 over 2, let's do that, 3 over 2 and multiply by a half, you're going to have 3 in the numerator, 4 in the denominator. That would be a of 3. This is a of 1. 3 over 2 is a of 2. 3/4 is a of 3. 3/8 would be a of 4, because if you took 3/4 and multiplied by a half, you'd get 3/8. So the common ratio is 1/2. That's what they're asking for. That would be the R in the formula. Okay. Next example. Find the next 3 terms in the sequence. This again is a geometric sequence. It's being multiplied by -2. The common ratio would be, I meant to write a negative there. The common ratio would be -2. So to predict the next term, what would go here would be 80. 40 times -2, -40 times -2 would give me 80. The next one would be -160. The next one would be +320 as I continue to multiply by -2. Okay, then it says determine whether each sequence is arithmetic or geometric. I started out with showing you, reminding you really what an arithmetic sequence is because they'll ask this kind of question. Is it one or the other? Well, to get from 162 to 52, one thing I could do is subtract a number, right? Would it be 88? I think it would be 88. But if I subtracted 88 again, I would not get 18. Notice that these are going down in value. In fact, what it is 1/3. Take 162 and multiply it by 1/3, you'll get 54. Multiply 54 by 1/3, you'll get 18. Multiply 18 by 1/3, and you'll get 6. So the common ratio, it's a geometric sequence. The common ratio is 1/3. Now let me say this too. A lot of people will look at this and go divide by 3. Now that's perfectly fine in order to find out the next term or whatever. 6 divided by 3 is 2. But when we want to put it into an explicit formula, you don't want to use the operation division. You want to use multiplication. So we ought to all know that times 1/3 is the same thing as saying divide by 3. 1/3 would be the number that went in for R in the explicit formula that I gave you in the notes. What about this one? 98, 101, 104, 107. These are clearly going up by 3, plus 3, plus 3, plus 3. So this one would be arithmetic. Not geometric, this one's arithmetic. A couple more examples. How about this one? Find the first, fifth, and 10th terms in the sequence that has the rule a of n is equal to -3 times 2 to the n minus 1. This is in the form that I just gave you, a of 1 times r to the n minus 1. A of 1 is the -3, r is the 2. And when they ask for the first, fifth, and 10th terms, basically they're asking for a of 1, a of 5, and a of 10. Now notice something too about a of 1. It's not a coincidence that it happens to appear right here in the sequence. The reason for that is if I plugged 1 in for n, I'm trying to find out what 1 is. 1 minus 1 is 0, and anything to the 0 power would be 1, and then that 1 times this term right here would be the number that you get. Okay? So even if I do that here in the example that they gave me, 1 minus 1 is 0, 2 to the 0 is 1, 1 times -3 is -3. It's not just a coincidence or something that somebody invented to put the first term here. In fact, that's what you get when you plug 1 in for n. Okay? A of 5 would be what you do when you get -3 times 2 to the 5 minus 1. And a of 10 would be what you get when you go -3 times 2 to the 10 minus 1. Now you may need your calculator for this, maybe for the last one and not the second one. 5 minus 1 is 4, 2 to the 4th is 16, and 16 times -3 is -48. I will use my calculator on the last one there. So that would be 2 to the 9th times -3. How about -1536? Okay, so a of 1 is -3, a of 2 is -48, a of 5 is -48, and a of 10 is -1536. One other thing, so that I make sure you understand this. This produces a sequence. That's a list of numbers. If I plug in 1, I get -3. That's because a of 1 is -3. If I plugged in 2, I'd get a different number. I'd get a different number at 3. I'd get a different number at 4. We figured out what 5 is. It's -48. A of 5 is -48. And then a of 6 would be a number, a of 7, a of 8, a of 9, a of 10. We weren't asked about those. 6, 7, 8, 9. A of 10 we were asked about, and that's -1536. So that's what you're really doing when you're asked for the first, fifth, and 10th terms, is you're kind of skipping over those that you weren't asked about by just plugging in the specific number. 1, 5, and 10. All right, I think there's one more example. Yeah, suppose you drop a tennis ball from a height of 2 meters. On each bounce, the ball reaches a height of 75% of its previous height. Write a rule for the height the ball reaches on each bounce in centimeters, and then what height will the ball reach on its third bounce? Well, first I will note that 2 meters is 200 centimeters. Because they're asking for an answer that's in centimeters, I'll go ahead and just make that calculation from the start. Okay, so here's the thing. When we drop the ball, the first distance down is 200. That's how far you're holding it off the ground. 75% of 200 is 150. 0.75 times 200 would be 150. That's where it would bounce to after one bounce. You take 150 and you multiply that by 0.75, you'll get 112.5. I'm actually doing this on my calculator right now, and I'm setting it up so that it does eventually, after two training sequences, 84.375, I could now just push enter, 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 and it would continue to give me the next number, the next number, the next number. 63.28125. The next one's 47.5 or so. Okay. This is a geometric sequence because from 200 to 150 is times 0.75 or 75%, and so is this, and on and on. Okay. What is the height of the ball after its third bounce? Now here's something that's a little bit tricky. It's not the third term. You see, 200 is a of 1. 150 is a of 2. This is a of 3, although that's not the answer. In fact, the answer is this one, a of 4. Why? Well, because 200 was not after any bounces. The first term is not part of the sequence when we're being asked about after the third bounce. After one bounce is a of 2. After two bounces is actually the number at a of 3. After 3 bounces, that would be this. So our answer is 84.375. Now, one more thing. Can we put it into this? A of n is equal to the first term, 200, times r, which we just found to be 0.75. I like to put it in parentheses just to set it apart. You don't have to the n minus 1. Okay? Now, understanding this example as you read it would compel you to plug a 4 in for n. And then what happens? 4 minus 1 is 3, and 200 ends up getting multiplied by 0.75 3 times. This is how exponents work. 200 times 0.75 times 0.75 times 0.75 would give me the fourth term. This is why you have to increment down 1. If you didn't do that, if you didn't have the minus 1 here, you'd be raising 0.75 to the fourth power, and you'd be multiplying 200 by 0.75 4 times when we only wanted to multiply it 3 times because it's after the third bounce. You plug in 4 here and do the math, it'll produce 84.375 centimeters. And there you go, centimeters. All right, thanks for tuning in.